Hey guys, welcome back to the channel. In this video I'm going to be going over IB Biology, topic 10.2. More specifically, we're going to be looking at a chi-squared test. A chi-squared test is a biological test that's used to determine whether the difference between observed and expected values is statistically significant. So we can test the presence of linked and unlinked genes. The first step in doing a chi-squared test is to identify two types of hypotheses. H0 is the null hypothesis, and it claims that there's no statistically significant difference between the observed and expected values. H1 is the alternate hypothesis, which does claim that there's a statistically significant difference between the observed and expected values. So maybe you may be wondering why this is important in biology, and more specifically 10.2. Well, in 10.2, we learn about linked and unlinked genes. So linked genes are genes that are on the same chromosome, right? If they're on the same chromosome, that means independent assortment does not occur. And this goes against the Mendelian inheritance. So for us to identify linked and unlinked genes, we need a chi-squared test. Specifically, if we have the alternate hypothesis being accepted, we find that these genes are unlinked. And if we find the alternate hypothesis being accepted, we find that these genes are linked. Here we have a dihybrid cross with the different genotypes. Phenotypes. Yeah. So we have big A, big B, little b, little a, big B, and little a, little b. Those are going to be our four different phenotypes, and that means the degrees of freedom are going to be 4 minus 1, which is going to be 3. So to identify the degrees of freedom, this is not always the case, but in the case of dihybrid crosses, you get the number of different phenotypes, which in this case is 4, and you subtract 1 from them and get 3. So if there were 3 different phenotypes, you'd have 2 degrees of freedom. That would be the DF value. And this value will come into play later, but take note of it for now. Let's say we did some sampling. Like, if you guys have heard of a quadrat, which is like a square, a sample area where we test different things. This can be like an area in a forest where we test for particular characteristics. Let's say that we found 711 different organisms with AB, type AB phenotype, 214 with big A, little b, 253 of little a, big B, 78 of little a, little b. Let's say those were what we observed. And theoretically, based on our expectations, perhaps we did a dihybrid cross and got the ratios. This is what we expected to get. So 694 for big A, big B, big A, little b, 238, little a, big B, 238, little a, little b, 86. So these are the expected ratios, expected frequencies, and these are the frequencies we have. So already looking at this, since the 2 bits in the middle are equal, in this case I can tell that this has been the result of a cross. Perhaps a 9:3:1 ratio. That's possible because you see like the 2 things are in the middle, but I don't think that's the ratio. It's something else. That's the ratio is relevant to this question, so we're gonna ignore that for now. But we have to calculate the O minus E values. So O minus E, 711 minus 694, that's going to be 17, I believe. Yeah. 214, take away 238, that's going to be negative 24. And then this is going to be negative 15. Wait, no, this one will be positive. So this one will be 15 by itself. This one will be negative 8. So we have these values, but what happens is we got to square the O minus E value, right? So 17, so I'm going to do that in my calculator and come back to you guys. So here I've gone through my calculator and entered the squared values of this. So for the OE values, we have to square in the chi-squared test because we have negative values and we can't really work with negative values for this circumstance. So when we square them, we get rid of the negative. So that's one way you can remember this step quite easily. Next, we have to calculate another value where we basically divide this O minus E squared value by the expected values. So I'm going to do that and I'll cut back to when I'm done. Now here I've inserted each of these values. So the O minus E value divided by the expected value for big A, big B, big A, little b, little a, big B, and little a, little b. The actual formula for chi-squared is sigma O minus E squared over E. So that means the sum of the observed minus expected value squared over expected. Sigma means sum of. So essentially it's the sum of all these values added together. So let's work it out. Okay, so I worked this value out to be 4.525. That's the value I got for chi-squared. Next we need a p-value table for our chi-squared. We have this value, but the way we interpret it is completely dependent on this table here. So remember how we said the degrees of freedom was the number of phenotypes minus 1, which is 3 in this case. This comes into play where we find the p-value table. The p-value table will often be provided with a question, so you guys don't need to worry about memorizing any of this information because that would be very brutal. So I've got this from BioNinja, and as you can see, there are these numbers on the top and numbers on the bottom. So the key numbers here are the p-values are going to be this top row, and the bottom row is going to be the actual chi-squared values. So the way to interpret the p-values is if you have 0.05, it's 5%. So that means there's a 5% chance that this result was not statistically significant but was actually due to chance, just random chance. And 0.025 means that there's a 2.5% chance that this was just random and not actually due to something statistically significant. So the lower this is, the lower the p-value, the better. Generally for biology, 0.05 p-value is what is desired. So if we have a chi-squared distribution value that is above 7.815, then that means we can interpret that there's a statistically significant difference between the observed and the expected values. So that means we can accept the alternate hypothesis. However, 4.525 is just slightly bigger than 0.25 and slightly smaller, slightly bigger than 4.110, but slightly smaller than, it's slightly bigger than 4.110 and smaller than 6.25. So it's going to lie somewhere in this range. So it's definitely not going to be less than a 10% chance for random variation to have caused this statistically significant difference. This difference between the observed and expected values. So that means since we did not get, since there's a higher than 5% chance that this was due to random variation, we cannot admit that that the difference between the observed and the expected values in this distribution were statistically significant. Therefore, we have to accept the alternate hypothesis. The null hypothesis, H0. Which claims that there's no statistically significant difference, so the genes are unlinked. So that's the conclusion we draw upon in this question. Say we did get a chi-squared value of 8.5. We'd first use and the degrees of freedom, of course, is 3, let's say. We look at the 3 degrees of freedom 3. There could be a table with multiple degrees of freedom rows, and then going out with each of these p-value columns. We can see that 8.5 would be above 0.05 and lower than 0.025. This column, that is. So that means the chance that there's random variation is going to be lower than 5%, but higher than 2.5%. So we'd still accept that because we have met this threshold of 5% as the maximum random chance for variation. But if we have a value, let's say, of 2.5, I'll do it here, 2.5, that's going to be in between these values, and we're going to be, between 50%, we're going to have less than 50% chance for random variation, and higher than 25% chance for random variation, being the cause of this difference between the observed and expected values. So again, that's not good enough. So always in biology, we're meant to look at values from 0.05 and above for the p-value. So when the chi-squared value, just to reiterate, is bigger than the 0.05 p-value, the chi-squared value, such as 7.815 in this case, then we accept the alternate hypothesis saying that these differences are statistically significant. However, if we have a chi-squared value that corresponds to a p-value that is higher than 0.05, say 0.25, then we cannot accept the alternate hypothesis. Instead, we must accept the null hypothesis, because we have to admit that there's no statistically significant difference between the observed and the expected values, so our genes are unlinked. More on unlinked and linked genes later, but that's going to be it for this video, guys. I hope you guys enjoyed. 10.2 linked genes, and more specifically chi-square test, is definitely one of the more difficult intuition-based topics or subtopics in IB biology. So if you guys have any questions, leave them down in the comments. And if you found this video helpful and would like to see similar content from YouTube, please like, subscribe, and comment any video ideas for future. Anyways, guys, that's Learnify signing out. Hope you guys have a good one.